let's get started. So welcome everyone, and thank you for joining our second webinar in the Tech Talk series dedicated to the software architecture. Before jumping into the interesting stuff, I just want to let you know that this webinar is going to be recorded and will be posted on our website in the upcoming days. We will also have a Q&A section at the end. And please post any question you have in the Q&A box. We will review them and answer them at the end of the presentation. So my name is Răzvan Lazar. I'm head of technology at Thoughtworks Romania, and I'll be co-hosting this event with my colleague and friend Cristi Dumitrescu, tech principal at Thoughtworks Romania. Joining us, Cristi.
Happy to be here.
And our guest today is Neal, director, software architect at Thoughtworks, very well-known speaker at dev conferences worldwide, an author of 8 books. And I will just mention here my 2 favorites, Building Evolutionary Architectures and Fundamentals of Software Architecture and Engineering Approach. Thank you for joining us today, Neal.
Thank you for having me. It's great to be here.
Pleasure is all ours. So we discussed in the previous webinar with Rebecca Parsons about the principles of evolutionary architecture. And we discussed about the utilities, the fitness functions, and the different architectural styles, the different messaging styles. We talked about modularization, granularity, decoupling, and also about the hard coupling forces, which makes our work difficult when we are trying to decouple things. Forces like transactions, for example. And it became quite apparent, the first rule that you, Neal, formulated in your book, which says that in software architecture, everything is a trade-off, which led us to the topic we have today, architecture, the hard parts. We are very, very excited about having you, Neal, today, and also about watching the premiere of this talk, because I understand this is the first time the material is going public. So thank you for that. And I have to ask you, what tools and practices do we have to support decisions when we are dealing with these trade-offs?
Well, that's exactly what I'll be talking about today is, one of the most difficult things in modern architectures is how to do trade-off analysis. And there are a bunch of really old heavyweight frameworks like ATAM, which is the architecture trade-off analysis method, and CBAM, the cost-benefit analysis method. But these are big, year-long governance policies with meetings and bureaucracy. And as an architect, I have a problem in an architecture. Should I use orchestration or choreography? ATAM is not going to help me with that. CBAM and all these heavyweight things are not going to help me with that. And so what we've done is actually put together a set of tools and a way of doing your own trade-off analysis in architectures. And that's exactly what I'll be talking about today. So,
sounds great.
We should do that. So let me steal the screen share and share my slides. You should be seeing my slides now. I say yes, architecture, the hard parts. There are 4 co-authors to our book, 3 Thoughtworkers and Mark Richards, myself and Mark. But Mark and I are the only 2 to put together the material today, which is why only our 2 pictures are there. What I'm going to give you today is a serious subset of the material in our upcoming book, Architecture, the Hard Parts, which looks like this. It will be released in November this year. And in fact, it is in tech review right now. So as Razvan said, you are one of the first groups in the world to see this material. And what we were doing when we wrote the Fundamentals of Software Architecture book, we kept coming up with examples that we would start digging into and then say, you know what, that's too difficult for the Fundamentals book. Let's set those aside. And by the time we ended the Fundamentals book, we had this huge stack of complex problems in software architecture. So we said, okay, why are those so complicated? Why are those problems so hard to figure out? And that was our task for this book, is to figure out why are some problems in software architecture, particularly distributed architecture, so difficult, and how do you make them less difficult? And so here is what we figured out in the very abstract, and then I'm going to spend the rest of this session today showing you how to make these ideas concrete. So it's really about modern trade-off analysis. How do you do trade-off analysis in architecture? Because one of the problems you have in architecture in general is that nothing in architecture can be generic. You know, it's when you look at a tool like Kafka or Kubernetes, you can download that tool and set some configuration parameters and start using it. But architecture is different because every company's architecture is a magical snowflake. It's a combination of platforms and technologies and old choices and new choices and legacy and commercial software and stuff we can't get rid of. Every one of those is a completely unique ecosystem. How do you do trade-off analysis in your completely unique ecosystem? You can't come up with a general silver bullet way of handling that. You have to handle it on a case-by-case basis. So here's exactly how you do it. So I'm going to give you the abstract way of building a trade-off framework, and then I'm going to use the generic problem of granularity and communication in microservices to illustrate how this works. So here is the technique for doing modern trade-off analysis. The first thing you do is have to find out what parts are coupled or complected together. Complect, there's no way that most of you who have English as a second language know the word complect unless you were in the closure world, because they use it in the closure world. It's an archaic English word, but it's perfect for this because it means things that are braided together. So think a braid of hair. It's very hard to trace a single hair through a braid of hair because they're all tangled up together. That's what complected really means. And so if you're trying to do a trade-off analysis for something, you have to find what parts are coupled together. And we're using in our book the simplest possible definition of coupling in software architecture, which is I am coupled to that thing if when that thing changes, I might have to change because of that. That is the simplest possible way of thinking about coupling is I may have to change if that thing changes, therefore I'm coupled to that thing. And so there's, you find out what parts are coupled together in this decision you're trying to make, and then analyze how they're coupled to one another. In other words, if I change this, what changes over here? So you're analyzing not only the coupling point, but then what impact that coupling has. And you'd like to get that either to a spectrum or a binary. And I'll show you what I mean by that in just a second. And then assess trade-offs to determine the impact of change when you make those tweaks to one thing versus another. And we'll actually build a matrix to talk about. Once you've built a matrix, you can say, okay, change this and see what impact that has on the rest of the thing. So we're going to build almost a spreadsheet view of architecture trade-offs around this idea. And this is all, of course, derived from our book, Software Architecture, the Hard Parts, and this idea of how do we figure this kind of stuff out. And the book is split into two parts. Pulling things apart and then putting things back together. We chose this structure because we realized as we looked at all of these examples we had and came up with, okay, here are all the difficult parts of software architecture we need to talk about. When we looked at them, they kind of fell into two piles, structural versus communication. And as you'll see, that actually became an important part of our decision framework about structure versus communication. So let's talk for a second about architectural modularity and modularity within a piece of software and software ecosystem, whether it's a monolith or something like microservices. So why would you consider breaking apart an application into smaller distributed components like this? So there are 5 drivers for changing the modularity of something in a software architecture and building smaller pieces. And let me show you the first of these. And this is actually my favorite metaphor for many things that constantly happen in the software development world. So you start with a simple tool that does one job beautifully and elegantly. And it's like, wow, that's an awesome tool. And you know what? It would be perfect if only it had scissors. Okay, now it's perfect. That's great. This is awesome. I'm using this for all kinds of stuff. But you know, every once in a while you need a corkscrew. So, okay, but now we're done. We're finished. It's good. This is exactly what we want. This looks like a really good tool, but ooh, push pin. You know, sometimes you need a push pin. So, okay, but now we're really done. We'll stop adding stuff now. It's good. It's really good until eventually they all become this. And notice that this still has a knife on it, but it's not useful as a knife anymore because literally the weight of all the extra features that have been added to it have made it very clumsy to try to pick this up and actually cut something with it as a knife. But this happens over and over again in the software world. That this is why, one of the reasons why you end up breaking things down into smaller pieces, because if you only have one bucket, one monolithic application, and you keep adding features to it, you eventually end up with something that looks a lot like this. So that's one of the drivers here, is breaking things down. For maintainability, it's a lot easier to maintain. Testing is a lot easier because you isolate the scope of testing. Deployment is easier because you can lower and make that scope smaller. So are things like scalability and fault tolerance. These operational architecture characteristics get a lot easier when you do that. And so when you think about restructuring an architecture, there's really a couple of choices you can make here. So is modularity justified? Should I even bother doing this? And if not, then you keep it as a monolith. Is decomposition feasible? And I'll show you a way to think about that in just a second. And if that's not, then you want to keep it as a monolith. If it is feasible, can you define components within it? And if you can, then you go through these patterns of component-based decomposition. Otherwise, you use this pattern that's called tactical forking. And at the end of this process, you end up with a distributed architecture. So the component-based decomposition, the idea here is you take your monolithic application, you identify and size the components inside it, gather common components together, and figure out what to do with those in terms of sharing or duplication, flatten them to get rid of some of the distinctions, and then analyze component dependencies so that you can create component domains, then pull those apart to create domain services, and keep breaking those down until you get to an appropriate size. Appropriate size being an interesting statement, I'm going to give you some guidelines for that sizing here in just a minute. And so the idea is, if you take something like this with a whole bunch of components in it, a lot of these have to do, for example, with tickets. And so I can build in a bunch of stuff around tickets. You'll notice login and notification is shared by a lot of things, so we can isolate those things, gradually restructure the internal components until we get enough separation between them to be able to isolate them and pull them apart, maybe put them behind a proxy so we can call them invisibly from a user interface without having to change it. And so that's the structural way to decompose an architecture like this. But what if the monolith that you've been given, when you're really honest with yourself, it's not really an architecture, it's really kind of a big ball of mud. It's really hard to analyze it, and this whole process of identifying internal components is basically impossible because it's just a big pile of code. So the alternative to this is this idea of tactical forking. This was named by our colleague in Quito, Ecuador, Fausto de la Torre. He's the one who gave the name to this pattern. Instead of trying to structurally decompose from inside, rather than extracting something, the idea of tactical forking is, let's remove everything except the thing we want. This is sort of like a sculptor. When you ask sculptors, how did you sculpt that beautiful animal out of that block of ice? They will frequently say things like, well, I just removed the ice that wasn't supposed to be there. And that's basically what you're doing in tactical forking. So the idea of tactical forking is you start with an application that you really want to split in part, where one part has two of these geometric shapes and the other just has one of them. And the first step is to clone the entire code base. This is the tactical fork, and give one complete code base to each team. And now over time, they're going to hack away the parts that they don't need for their ultimate goal and gradually diminish those until you finally end up with two distributed applications that have more or less the right stuff in them, but gotten to in a very subtractive kind of way. Now, the problem with this, of course, is that none of these will be beautiful, elegant, outcomes. None of these will be really nicely factored and a code that you're proud of, but it will work. There'll be a lot of dead code probably sticking around that you can't really get rid of because it's kind of coupled in ways that you can't delete, but you don't want to take the time to untangle it. So, but it is a way. And of course, the benefit is you get to start working on it right away. And so tactical forking for an application like this would say, okay, there's not enough internal structure to do that restructuring. So let's just clone the entire thing and start chewing away the pieces that we don't need and end up finally with two distributed components that have more or less the right distribution of stuff in them. This would give me a way to get back to better modularity, etc. So let's talk now about one level in to the architecture and talk about components and component-based design, and talk a little bit about this picture. So when you go through the process I just talked about, let's say that I'm trying to determine what the target architecture should be for either a new system or an existing one that I'm doing a migration for. And so one of the things that we talk about in our Fundamentals of Software Architecture book is this idea of architecture characteristics, which is some people call them non-functional requirements or system quality attributes, or there are lots of names for these things. Cross-functional requirements is another one. Whatever you call them, that's an important part of your consideration of how and when you should break things down. So the first step here in this flowchart, let me zoom in on this so you can see it a little bit better. The first step here in trying to choose what my target architecture should be, either for new or existing or for migration, is look at the domain analysis and the architecture characteristics to determine the first question: do I have one set of architecture characteristics or do I have multiple sets of architecture characteristics? Let me give you a quick example of this. So one of the examples we show in some of our workshops is the going, gone example problem. And if you walk through this, you'll see that it has these general architecture characteristics. And furthermore, if you go through a design domain analysis, for example, using something like event storming and domain-driven design, you end up with a set of components that look more or less like this. Now, when you do this domain exercise, you'll notice that we have the one that's in red there, bid capture, because we have two roles in this architecture: bidders, and there are hundreds or thousands per auction, and an auctioneer, who's the one who's actually conducting the auction. But after you've done the domain analysis, you now need to go back and look at the impact that architecture characteristics may have here. And you'll notice that when you think about that, I actually need two capture components. I need bid capture, but I also need auctioneer capture, because from a domain standpoint, it's the same functionality, but from an architecture characteristic standpoint, they're very different. Because think about scalability for a second. I have hundreds or thousands of bidders, which means I need scalability for that connection, but I only ever have one auctioneer. So I don't need scalability for the auctioneer. What about reliability? It's certainly bad if somebody drops a connection while they're trying to interact with my auction and have to relog back on, if one of the bidders, if that happens to them. But if the connection for the auctioneer drops, the auction's over and I can't make money anymore. The point of this is there are distinct architecture characteristics that you need for those two parts of your architecture, and that drives you toward two separate components. And that's exactly what I mean by this first analysis. Look at architecture characteristics and domain analysis, and that will give you either one set of architecture characteristics. If that's the case, you can safely choose a monolithic architectural style, which is much simpler in many ways. If you have more than one set of architecture characteristics, like we just discovered, then you need a distributed architecture. The next step then is to figure out what the granularity of those services should be. And that's my next subject, is this granularity of services. Razvan was nice enough to mention one of my previous books, which is here, Building Evolution Architectures, which I wrote with Dr. Rebecca Parsons. This is also a brand new news that hardly anybody knows about. We've been asked by O'Reilly to do a second edition of the book. So that looks like what I'll be working on the second half of this year is Building Evolutionary Architecture second edition, which is nice because we've got a million more examples of this since that book came out in 2017. And the main thrust of this book was the definition and a few examples of this idea of architectural fitness functions as a way of automating architectural governance within architecture. But one of the things that we also wanted to do in that book was to analyze particular architecture styles or topologies as to how evolvable they were, because we had a hypothesis that some topologies give you more evolvability than others. And toward that end, we looked at a lot of existing metrics and couldn't find one that was suitable for what we wanted, mostly because they only looked at code and didn't look at external dependencies like data and search engines and things like that do have an impact on some of your architecture characteristics. And so toward that end, we created this new measure called an architecture quantum. And here was our definition in the Building Evolution Architectures book. An architectural quantum is an independently deployable component with high functional cohesion. But once that book came out, we continued to use this quantum idea as an analysis technique. And it turns out it's very, very useful because, well, for several reasons I'll get into. And so we've expanded the definition for the Architecture of the Hard Parts book. And here's the new definition. It's still independently deployable artifact with high functional cohesion. So that's still the same as before, but we've added a lot of nuance to this definition. There was an interesting book that was written back in 1993 called What Every Programmer Should Know About Object-Oriented Programming by Peter Gillard-Moss, I believe, is the author of that book. No, that's the name of one of our colleagues, Peter Miller-Jones. I knew it was one of those three name things. Anyway, he wrote this interesting book back in 1993, most of which was about an object-oriented design technique that nobody really uses, even in 1993. But one of the fascinating things in that book is he defined this idea of connaissance. And there's a great website called connaissance.io that's worth looking at because it's a great vocabulary for describing how things are coupled together. But we didn't use that either. But there was one concept that was very, very perceptive from that book. And that was his realization that in architecture, so here's the first braid we're going to untangle from our complected soft distributed architecture. The first braid we're going to entangle is static versus dynamic coupling. So that's the static versus dynamic definition you see here. So let's talk about static coupling in architecture. So, and we can talk about the static coupling between quanta. So the idea of an architecture quanta is this deployable unit within software. And part of this is a measure of how things are coupled within an architecture. And so, for example, these are all a single quantum. So anything that has a single coupling point, like a single relational database, is always going to be a single architectural quantum. So the layered monolith, modular monolith, microkernel are all a single quantum because they're all coupled to a single coupling point. Even an event-driven architecture is, if it is only talking to a single relational database, is still a single quantum, because part of what we're measuring here, so can I make part of this architecture more performant than another part? And the governor here is always going to be that single database. And so that's going to be the thing that limits my ability to improve the scalability of one part of this versus another. I really need a distributed architecture for that. Even something like a service-based architecture that uses a single database is a single quantum. So let's talk about some things that have more than one quantum. And this is a Latin word, so quantum is one of them and quanta is more than one of them. And here's an example of an event-driven architecture that has two distinct quanta that each have their own database. And you'll notice only asynchronous communication is passing between the two quanta here. And that's important as we talk about communication here in just a second. One of the interesting characteristics of microservice architectures is that if you follow the goal of microservices, then every service forms its own quantum because it's highly decoupled from the others. at the architecture level at least, although if you stick all of this behind a single synchronous user interface, then you're back to a single quantum, because that's the coupling point. So part of this is measuring how things are coupled together from a wiring standpoint, from a dependency standpoint in the architecture. This is one of the reasons why there's a lot of interest around micro front ends. Here's an article from Martin Fowler's website about this idea of the architecture characteristics of the front end components are related to the services, not to the user interface layer. And these are essentially independent of the UI layer, which is basically just a canvas that these components paint onto. And so the idea of the static quantum measure is this is how static dependencies resolve themselves within a distributed architecture. And so the static quantum includes everything required to bootstrap something like a service. So it's the code, it's the container, it's the database. If you are using an event-driven architecture and need a message broker, then the broker is part of the static quantum. It's everything required to bootstrap it. So all the transitive dependencies that get delivered through Maven or NuGet or something like that is part of that static quantum. Any integration points in your integration architecture. And notice that this is a useful view of your architecture all by itself. We have a large client who one of the things they're trying to do is figure out the impact of change across this big integration architecture. So they created this chart of how things are coupled to one another. If I change this, then I may have to watch and make sure I change this other thing. Well, they've basically created a static quantum diagram of their architecture of dependencies. And so the way you think about this is how things are wired and what's required to bootstrap something like a service in microservices. Now, if I want that service to collaborate in some workflow, that other service is not part of the static quantum. It's going to be part of the dynamic quantum, what I call it. The static quantum is really just about dependencies and transitive dependencies required to bootstrap something like a service in a microservice architecture. So that's the static part of this. The dynamic part of this is our real application of this framework that I talked about. So as we looked at these lots and lots and lots of examples, both from that we had put together that were generic examples to illustrate something, but also lots and lots of examples derived from our work with client projects, we tried to figure out, okay, generically in microservices, communication, what are the forces that are coupled together? In other words, if I have this and I change this other thing, does it break? And here are the three forces that we figured out that are true across all distributed architectures. Now, this is not exhaustive because in a particular case, you may add more, but it seems like these three are always present. And the first of these is consistency. Is it atomic or is it some flavor of eventual consistency? So notice we say atomic here, not acid, because you never get acid in a distributed architecture because you can't get the I. Isolation is impossible in a distributed architecture, but you can get the A, C, and D, which is basically atomic. And this is basically kind of hard and crunchy on one end and then a big spectrum on the other end, because eventual consistency can be very eventual and very, loose definition of consistent, but very hard at the atomic end of this. So that's one of those forces is consistency. The second force is communication. Is it synchronous or asynchronous? And this is basically a binary, one or the other. And notice that if I'm talking about synchronous versus asynchronous communication, atomicity is much easier with synchronous than it is asynchronous. So see how they're coupled together. That's how I define these things, that if I change this, it has an impact on this other one. And the third force is coordination. Am I using orchestration or am I using choreography? And this was a hard one for us to come up with, but we noticed that if you keep looking at all these examples, the ones with complex workflows hugely benefit from orchestration. I'm going to show you exactly why that is here in just a second. What's interesting about these three forces is that you cannot change any of these independently, because when you change one of these, it changes the others. That's the definition of them being coupled together, which means that these are basically conjoined in something like a three-dimensional space. And what's interesting about this is that we're talking about distributed architectures here, but what happens if I want to think of this as a non-distributed architecture? So in other words, what is the behavior at the origin of this graph? Mediated, synchronous, atomic, that's a monolithic architecture. So collapsing it to the singularity means that you're back into a monolithic architecture and you're not in a distributed architecture anymore. So that's exactly the characteristics you get in a monolith. The other thing that's interesting about this as a way of thinking about this process is that if you have a very, very simple workflow, very, very simple mediation, that dimension basically just collapses away and you're back to the two-dimensional problem of synchronicity versus consistency. So we're going to use this framework to talk about how to figure out the best communication style between services in microservices here in the second part of what we're going to talk about. So that's our newest definition of quantum. And what's interesting about that is that it's really the scope of architecture characteristics. And we saw an example of that when we looked at our bidder example, because you can see that auctioneer capture versus bid capture, those are distinct components, and the scope of those architecture characteristics is at that quantum level. So let's talk about this idea in two parts now remaining: static coupling and dynamic coupling. Let's talk about static coupling first and answer this question. What is the correct level of granularity for my service in a microservice architecture? This is one of the commonest questions we get these days. And almost every developer, if they follow their instinct, gets this wrong. And this is one of the reasons why it's really important to iterate on design, because nobody gets this right first time. So, but if you iterate, you can get a lot closer. And I'm going to show you how to iterate on this design, because it turns out that when you look at component granularity within a distributed architecture, you have two opposing forces. You have what are called disintegrators. These are things that encourage you to take big things and break them down into smaller things. And most developers only follow their disintegrator instinct. But you also have integrators, which are things that encourage you to bundle things back together into something that's not so small. And let's talk about each of those. There are 5 disintegrators and 3 integrators. And so this is how you decide and iterate to get to the size of your services. So let's talk about the disintegrators. The first of these is the most obvious, which is service functionality, which is domain functionality. So let's say that I have, for example, a notification service and have SMS, text, email, and postal letter. If I follow the service functionality disintegrator, then I will probably break this down into 3 distinct services: SMS, email, and letter service, because I'm just following now the service functionality. But what about this one from a service functionality standpoint? Customer service, profile, preferences, and comments. Should I break that down into 3 distinct services? Maybe. But again, this gets back to, what is the real definition of a customer here? Is it really those 3 parts, or are there more parts? And so, but this is an example of taking service functionality and breaking things down based on service functionality. The second disintegrator is code volatility. And this is really about how fast code changes. This is a measure that you can get out of a lot of source code repos. And so let's say that for various domain reasons that our SMS code almost never changes, SMS and email, but our postal changes all the time because of configuration and postal rules and a bunch of other stuff. And so following volatility-based decomposition, you might say, okay, well, electronic notification versus letter notification. This is a good spot for me to pause for just a moment to talk about why you should not evangelize things in software architecture, because there is a small group within the software development ecosystem that will argue until the veins stick out on their forehead that the only way you should ever break anything apart is volatility-based decomposition. There's a whole movement. Yuval Lowry, he's a very smart guy, is leading this movement around volatility-based decomposition. And people stand up and shout at you that that's the only way to do stuff, which is impossibly naive. But what happens is Yuval is in a problem space like finance, where volatility is a big deal and it's a clear disintegrator for them. And the problem is when you're in one of those spaces, it becomes easy to believe and extrapolate that all spaces are like the space I'm in. Everything in software architecture is a trade-off. Volatility is one of those drivers, but it cannot be the only driver ever. You can't give global generic advice in architecture like always only use volatility-based decomposition. Sometimes you do, and sometimes you don't. But there's a larger issue here of stop evangelizing things as an architect, because you're only going to get yourself in trouble. There's a group of people that used to be called Rastafarians who believed as an organizing philosophy that Roy Fielding, when he created his doctoral dissertation, solved all the problems that can ever be solved on planet Earth with rest. And there are these long arguments about which of the 4 verbs do you use to solve this particular overarching problem in software architecture. And it's like, it's really just a transport protocol. Rastafarians were one group. The gRPC fanatics are one right now who believe that the solution to everything in architecture is gRPC. It's very nice for a lot of things, but it's not the universal answer for everything. Reactive is another one of those semi-religions in the software development world. Your job as an architect is not to find things to evangelize. Your job as an architect is, given some situation, can I assess the objective trade-offs on either side? If it's architecture, there have to be trade-offs because everything has trade-offs. And the more you hone your skill of figuring out what those trade-offs are, the more service you give to the project you're on, and the less you're setting yourself up for, because people evangelize things, they overemphasize the positive and underemphasize the negative, and the negative always comes back to bite you. If you're always honest and upfront with every one of your decisions, then you have a lot less of that happening. So volatility is one way to decompose things, but it is not the only way to decompose things. So never fall into the trap of always or never. So the third one of our disintegrators are, this says scalability and throughput, but this is more broadly any of the operational architecture characteristics: reliability, scalability, elasticity, throughput, all of those that have an overlap with something like operations. So for example, let's say that I look at my notification service and I observe that this is the number of requests that I get. Well, that may be the driver for me to break those things down. And, you know, the 1 request a minute, I can create an underpowered Raspberry Pi and deploy my code on that with no problem, but probably not the 220,000 a minute version of that. The fourth of these is fault tolerance and the availability and reliability side of the operational characteristics. So let's say that email has a bad habit of collapsing. And of course, when that happens in my notification service, it takes the whole thing down. And so if one of those is a lot more volatile or a lot more less reliable than the other, volatility is about rate of change. This is about operational reliability. If I set this up so that email is isolated, then if it goes down and takes that whole service down, the other 2 services still work fine. So that isolation might be one reason. And of course, one of these disintegrators that's always there is something like data security and security in general. And if I have a profile service that has some semi-sensitive info and some very sensitive financial info, I might very well want to break those into multiple parts. So those are my 5 disintegrators. But what about the integrators? This is the thing that a lot of developers miss. And the problem they run into is they end up creating a very, very fine-grained microservice architecture, but then to get it to do useful work, they end up stitching all those microservices together and everything's really slow. And now they're trying to do transactions at the architecture level, and distributed transactions are a nightmare to get to work, and that's even slower. And what are we doing microservices for anyway? This seems like a nightmare. And so here are the integrators that bring those things back together. There are 3 of these. And the first of these is database transactions. This is actually a good indicator of where your bounded context should be, because someone in your problem domain has said these things need to atomically work together. And so, for example, if I have a profile service and a password service that I need to pass information over to, you never want to try to do this distributed transaction in a distributed architecture. Never is a strong word, but you want to try to avoid this as much as possible. Now, this is what's referred to as a saga, and I'll talk about all the possible flavors of sagas when we talk about dynamic communication and the ones you want to do and the ones you definitely do not want to do. But you do not want to do this in a distributed architecture at all, because the error possibilities are endless and you'll never end up chasing all down. And so rather than breaking those things down and artificially making things difficult for yourself, why not just have those as one service with one database? Now the transactional problem goes away because the transactional boundary happens within the service. The second one of these is data dependencies. This is one of the things that many books about software architecture ignore, is data and data dependencies, but we're not. In fact, one of our co-authors is Pramod Sadalge, who is the well-known author of the Refactoring Databases book. We're trying to amplify the impact that data and data structures have on the decisions you make in architecture. And here's a great example. So I have these 3 services, function A, B, and C, but they are mapped to these 6 tables. And I want to break these down into smaller distributed components. And so let's look and see how these things are mapped. And so it looks like function A is talking to all of these tables, writing to them. B is writing and reading from those, and C is writing and reading from that one. Okay, so now let's take it and decompose our tables just like we did our architecture. So, okay, 1, 2, 4, and 6 move over here to service A. That looks great. That works. 3 moves over here to service B, and 5 moves over here to service C. And that's great. We're finished and everything is done. Oh, there's some arrows left over. Well, that's not good. I got to fix all the arrows. So, well, I could just have service B connect directly to the number 5 table in that other service. Could. It's a really, really bad idea. This violates the idea, the core principle in microservices about bounded context, because now I'm wiring one service to the implementation details of another service. This is the worst form of coupling, because this is a very brittle connection between these 2. If service C changes one of the columns on one of their tables, it breaks another completely unrelated service, which is exactly what you're trying to get away from in microservices. And of course, I'd have to do this, that's a nightmare. Could do this, have them collaborate and just send the information back and forth, and that would work. Problem is, and this is where you run into a lot of performance issues in microservices, when you break things down too small, calls on the network are way slower than calls internally, an order of magnitude slower. And if these are really chatty and have to do this a lot, this is going to be really slow. Instead, why are you artificially making it difficult? Just bundle those into the same service. And now all of those issues go away. The data dependencies go away, the transactionality goes away, the read and write stuff goes away, and I've increased the performance in my architecture. The only reason you wouldn't want to do this is if B and C really fundamentally did need to have different architecture characteristics, like different levels of security or different levels of scalability. Then you'd be forced to continue to break them apart and figure out how to stitch up that data dependency. But this is obviously the easier way to do that. And the thing that gets you to this is the third one. which is workflow and choreography, which is what we're actually going to talk about next. So consider this. So let's say that I break this down into a bunch of services. But now I've got to get them to do useful work. And so I end up stitching them all back together. Which of these is going to have higher performance? The one on the left is going to be way faster than the one on the right, because those internal method calls are an order of magnitude faster than these REST or event calls or something like that within a distributed architecture. So, okay, this is going to be slow. And okay, now what about this? So my customer makes a request here and it starts this chain of, uh-oh. Uh-oh. I haven't really bought myself any advantages of going to a distributed architecture because it's just as fragile as the single service was. Because if one of these crash and they all have wired dependencies to each other, they're all going to crash. Responsiveness and performance. This is the thing I was talking about before. 1500 milliseconds to make a request here. But now I've got to make all these hops. And of course, each of these hops have latency back then to 4,500 milliseconds. This is not uncommon to get these kind of changes between things. Reliability and data consistency. What if that service goes away? What state is my data in right now? I don't know, but I have to write some code to fix it, which is the issue from an architectural standpoint. And so this is one of the great integrators is I've broken down a whole bunch of services too small, and now it's causing me all these headaches. We should just bundle them back together, and all of these workflow and choreography issues go away. So those are the structural disintegrators and integrators. And see, this is exactly how you do the thing I was talking about before, which is iterate on the structural design. You put together your first pass at what we think the component boundaries are going to be using disintegrators, but then look to see if you created any problems for yourself and reapply some of the integrators to change the scope back again. Look at data dependencies, which is a whole separate exercise, because almost always when you do a deep analysis of those data dependencies, it causes things to grow back together in a useful way, because creating components that are too small is actually more damaging to your architecture than not creating them small enough, because you get too small and you get all the issues that we were just talking about. So let's talk about the other part of this, which is communication. We've been talking about wiring. Now let's talk about communication and putting things back together. This is actually, there was a famous quote by Dijkstra that was on the first slide, which is about, it seems like our instinct in architecture is to break things down, and we break things down to the point where we have to wire them back together to get them to do useful work. And so let's look at that issue of getting them to do useful work and return to this thing that we were talking about before in my quantum analysis. Sorry, I'm doing a subset of slides here. So let's first talk about synchronous versus asynchronous communication. Remember, this is one of the forces that we identified here, which was communication. So let's talk about synchronous versus asynchronous and what impact that has on a distributed architecture. So for our purposes, again, we're trying to use the simplest definition of these things rather than get in the weeds of all the, the possible ways to define stuff. So for us, a synchronous call is one where the caller waits and blocks for a response, and an asynchronous call is where you make the call and get the response asynchronously. So the typical way you would implement this is post a message to a message queue and return instantly, and then get a call back on that message queue when the response is done. But of course, there are lots of different ways to implement that. And universally for us, we do synchronous calls in solid arrows and asynchronous in dotted arrows. But we try not to overlay too much protocol stuff on here unless it's pertinent. And here's a case where it's pertinent. So for example, a synchronous REST call, 50 milliseconds to make the call, 1700 milliseconds to respond to it, and then another 50 milliseconds to send it back. So that's an 1800 millisecond round trip. But notice something interesting here. If I'm in a distributed architecture and the green service is operating at 1/10 of the scale of the yellow service, is this going to work? Let's say that the yellow service finishes 10 transactions all at once and starts trying to send those over to the green service. The first one will work and the other 9 will time out because it's waiting for that response and it's synchronously blocked. And so this is one of the impacts of synchronous calls in a distributed architecture like microservices. And this is purely accidental. We didn't plan for this to happen, but it turns out that it did. We can talk about dynamic quantum entanglement, which is a real thing in the physics world, and it's a real thing for us too, because during the course of a synchronous call, the performance and other operational architecture characteristics are bound together between these two services. As soon as the call's over, they're free again. But during synchronous calls, they have to have some similar level of operational architecture characteristics, or you have a reliability nightmare. And so that means even in things like microservices, if you're making a single, synchronous call, you're going to have that exact same impact. So for example, if I call using REST between two services, I temporarily bind their architecture characteristics together during that call. So they're no longer independent just for that call. But that's not true for asynchronous calls, because for asynchronous calls, that message queue can act as a buffer. So in the scenario I was talking about before, where the one on the left is operating at 10 times the scale of the one on the right, if that scale is elastic and I get bursts of new requests, then the message queue can actually handle those one at a time and allow me to pave over the differences. So asynchronous communication allows you a lot of flexibility in a distributed architecture when you have things operating at different scales, different performance, because it gives you that level of indirection that paves over some of these differences and creates a less brittle, more reliable architecture. For example, even with something like micro front ends, if I have two quanta that call each other asynchronously, they can be completely independent from one another. But if they call each other synchronously, they are temporarily bound together during that call because they need to have matching architecture characteristics, or at least close. So let's talk about some of the trade-offs of synchronous versus asynchronous communication. So it can have a performance impact on really highly interactive systems if you go synchronous. It creates these dynamic quantum entanglements, which means you have to carefully align the operational characteristics of your services in that case. And it can create some limits in distributed architectures, which we'll dig into next. But on the plus side, really easy to model transactional behavior. Transactions and other similar things are much easier to think about synchronously, because asynchronous means you're in a multi-threaded world and that's hard to think about. It looks like non-distributed method calls, so it's, again, easier to think about and therefore a lot easier to implement. Asynchronous, more complex to build and debug, and it presents a lot of difficulties for doing transactional stuff. So it's much easier if you're doing eventual consistency or base. And workflowy kind of things like error handling become a lot more difficult in asynchronous. And we'll see the impact of that in just a second. On the plus side, really highly decoupled systems. In fact, there are 3 ways to decouple things. This is one of them. Really common performance tuning technique, particularly in architectures like microservices that have performance issues. And it gives you really good high performance and scale. So let's talk about what we mean by this and talk about this fundamental question. I'm in microservices. Should I use orchestration or choreography? So this is the third one of our pieces. We talked about consistency, we talked about communication, now we're talking about coordination. So let's talk about both of these and then we'll make some decisions about them. So let's look at, so orchestration, of course, has an orchestrator, a mediator component that is responsible for coordinating that workflow. So when we talk about workflow, that's both the happy path and any boundary conditions and any error conditions that happen. So all of those make up a workflow. And in orchestration, you have a mediator component that manages that. So notice that you'd never have a global mediator in a microservice architecture. So like an enterprise service bus that does mediation for the entire architecture, because that's an extreme coupling. That would be part of the quantum for every single service, which means that you don't have, you have a single quantum and you have a distributed monolith, basically. So, but you can often have a mediator per workflow. And of course, the opposite of that is choreography, where there is no central coordination. So let's look at when you would choose one versus the other. So one of this is around workflow optimization. The more complex your workflows are, the more useful an orchestrator is. And error handling is much more difficult in choreography. So that's easier for an orchestrator, and state management. So let's look at those three impacts that orchestration have. And let's look at two sample workflows, one in orchestration and one in choreography. So let's say I'm placing an order. I have my order placement orchestrator who goes to the order placement service. It updates the order placement and lets the order placement orchestrator know, and it updates its state to created and posts a message back to the consumer. Okay, we've placed your order. It then makes a call to payment, gets order paid, gets that back and moves the state, internal state, to payment applied. Now it makes an asynchronous call to fulfillment. We need to ship an order to these people, gets an acknowledgement back that, okay, we're going to ship it. There's the order shipped status change. And now finally, let's notify them that their order has shipped. And so that's the end of our workflow. So that's what the happy path looks for. So let's look at a couple of error scenarios. And the first one is payment rejected. Well, when payment is rejected, when I try to do payment, I get card expired. This now comes back and I send a payment rejected message to my customer saying, hey, I'm sorry, your card's expired. Would you like to update your details? The second error scenario is back order, because I don't have inventory. So there, when I try to call fulfillment, it turns out that it's back ordered. So now a message comes back, say, sorry, we don't have it. Now I need to send a message to the customer to tell them that it's back ordered. And I need to issue a refund to the payment service, because that's already executed before this happens as well. So notice that when I start thinking about the entirety of the workflow, complexity comes in. And one interesting thing to note here is that for the entire workflow, I didn't need any additional communication points above and beyond what I started with. And so the architectural solution was sufficient. And the error handling was all just design. Notice too that I have a state owner for this workflow. So at any point, if I want to know what is happening with my order, I can query the state owner and find out. And so again, no additional communication points required to allow me to do that. So let's look at choreography and the same workflow in choreography. Place an order, order placement service, make a record. Okay, order placed, asynchronous call to payment. Okay, order paid, asynchronous call to fulfillment, asynchronous call over to email, done. Go back one. Wow, that looks really nice, doesn't it? But notice what happens when we start talking about error handling. I noticed that when I talk about, order placement notifies payment service, it may not even be that. It may just post a message to a message queue and say, hey, I just had an order placed. Anybody interested in that? And payment picks it up and somebody else picks it up. But let's look at the error conditions. What about payment rejected? Well, if card is expired, now payment has to tell email service to send them a notice about that. And it also has to update order placement if the order has already been updated in order placement. What about the back order? Well, now I'm further along in my workflow. So now back order has to go back and say, okay, refund it and email them to tell them that I don't have what they wanted. Notice that when I think about the entirety of the workflow, I have to add all these communication points back in that was there in the original orchestrated version. So we talk about this distinction in our book between semantic coupling versus implementation coupling. And this is a good example of, there's a certain amount of semantic coupling in this workflow. I've got to have an order placement service. I have something about payment. I have something about fulfillment. I have something about notification. That's just the fundamentals of my domain. And I can't get rid of some of that semantic coupling by implementing it a different way. I can make it worse, but I can't make it better. And so even trying to get rid of it, it all comes back by the time you end back all of the error handling, et cetera. And of course, if I have to worry about state ownership, if this guy is the state owner, then it makes it even worse because now they have to update this guy because it's owning the state of the order. And now they all have to update him when something breaks. And again, more additional communication points. So when you first look at choreography, it's like, oh, that's awesome. But then you start looking at all of the error scenarios. And it's like, ooh, that's getting a lot less attractive now. So let's talk about the trade-offs between workflow-based choreography versus orchestration. Choreography, you get much better responsiveness and scalability and fault tolerance and decoupling. This is a very decoupled way of thinking about things. But you've got to build a distributed workflow. And not having an orchestrator there means that workflow information has to go somewhere. You have to worry about state management. You have to worry about error handling and recoverability and all those issues we just talked about. Orchestration is really great if you have a complex or centralized workflow. If you have a lot of error handling scenarios, it works a lot better. It's a lot easier to recover. State management is a lot easier and queryable in Orchestrator, but it's not as responsive. It's more coupled because you have a bottleneck now. So fault tolerance becomes an issue. It's not as scalable, and you're more highly coupled than you would be because now you've got a component that is specifically coupled to several other domain components. And so really what this boils down to is which of these is more important, responsiveness and scalability with choreography, and you deal with the headaches versus workflow control and error handling in orchestration, and you deal with the shortcomings. So now that you've seen examples of those, let's actually do some analysis. And this is the coupling stuff that I was talking about before: consistency, communication, and coordination. So when you think about this as a conjoined space, so this is two possibilities taken three ways. My minor was in statistics, but I don't need a minor in statistics to tell me there are 8 possible combinations. And so let's analyze them all. Remember what I said when I was talking about this process that we go through here. Find out which parts are complected together. These three, the 3 C's are complected together. Analyze how they're coupled together, and then assess the trade-offs. So I can actually build a matrix here for all possible values of communication, consistency, and coordination, and see what that does to the rest of my decision process. And we've given names to all these things, so I'll talk about each of them in turn. The first of these we call the epic saga. And this is exactly what Chris Richardson talks about when he talks about a saga in his microservice patterns book. Notice this is atomic consistency, synchronous communication, and mediated coordination. This is trying to mimic a non-distributed architecture. Remember, the origin is a non-distributed architecture. This is trying to snuggle up as close to the origin as it possibly can. For each of these architectures, we have what we call this isomorphic diagram, which is not every possible workflow. It's the distinguishing workflow, the one that sets it apart from the others. And so notice the blue box here is atomicity. That's our transactional boundary. And we're saying that this whole workflow needs to be atomic, which means that if that mediator, when it tries to call the third service, fails, it has to send compensating transactions back to the other services, and it all has to happen within the scope of that transaction or not at all, which could be very slow, because if one of those services is temporarily down, it has to retry until that service comes back up. So any kind of global transactionality like this has a huge impact on responsiveness. And so for each of these, we have these ratings. Coupling for this is very high. That's our highest value, because it turns out that when you look at these 3 forces, the forces that increase coupling are atomic transactions, mediation, and synchronous. This has all 3 of those. This is as coupled as you can be in a distributed architecture. But complexity is low because you're modeling a monolith, and it's easy to understand that. Responsiveness is also low because that mediator has to do all that work in case something goes wrong, that slows everything down. And scale and elasticity is about as low as you can get. And this is one of the problems if you're trying to build microservices for scale, you end up doing these sagas and everything is slow and you can't figure out why. So we'll talk about a couple of alternatives that are better than this in a second. The second one of these is a phone tag saga. And what we've done here is changed it from mediated to choreographed. And so here, this is the same problem we had before, just more complicated because I don't have a mediator now. So if one of these services fails, it has to be smart enough to send compensating transactions requests to the other ones. And so each of these domain services has to have a lot more workflow information in them because I don't have a mediator there to hold that workflow information. So I have the same transactionality problem, but now I have more complexity because I don't have a mediator. This is mostly a mistake that architects make because they build the epic saga and they go, wow, it's really slow. Hey, one of the ways I've heard to speed things up is to change from mediation to choreography. And they end up making it worse in some cases. Coupling is high here, complexity is high, responsiveness and scale are both low because that blue box slows everything down, that transactional coordination. And now these are more complicated because of that. A fairy tale saga is a friendly story that has a happy ending. And this is a fairy tale. And notice the big change here is we've moved from atomic to eventual consistency. And this is actually what most people think about when they think about microservice communication. This is, in fact, the orchestration version I just showed you before, where each service owns its own atomicity or transactional boundary. And so notice I still have a mediator here, but now if an error causes a rollback, the mediator can go back and tell each one to update themselves, but it doesn't have to do all or nothing. And so the top two may actually be out of sync for a time period, but we're in eventual consistency, not transactionality. And so that's okay. And so this is tolerating a little bit of inconsistency over time to let the mediator go back and fix all those compensating transactions. So now we have high coupling because we still have a mediator here. We've actually only reduced one of the coupling drivers, which is at atomic transactions. Very low complexity. Very easy to think about this because transactionality is easier, synchronous is easier, and mediation is easier. So that's the lowest value for complexity. This is the easiest thing to reason about. Responsiveness is medium and scale and elasticity is high. And so this is actually what a lot of people think about when they think about communication and orchestrated communication in microservices when you don't have that atomic transaction thing going. Time travel. This is synchronous communication, choreography, and eventual consistency. And so this is a really good architecture for a pipeline, that kind of chain of responsibility, kind of I have a pipeline of things that need to apply in a single unidirectional kind of way. Because all of these guys, there's no mediator here. The transactions are at the domain level. If an error occurs, they have to synchronize themselves using synchronous calls, just like we saw in the others. So the domain services have to be a bit more complex here. So this is basically just like the time travel saga, or rather, sorry, the phone tag saga, just with choreography instead of mediation. And so medium coupling, low complexity, medium responsiveness, and high scale. We're getting higher scale. The more we reduce that transactional boundary, the more scale tends to come up. Fantasy fiction, we're getting into more and more unlikely scenarios. Just because these patterns are possible doesn't necessarily mean they're a good idea. And this is another one of those anti-patterns that people fall into. You start with an epic saga and you realize it's really slow, and you go, oh, I've heard that if you make things asynchronous, it's faster. And so you do that without changing anything else. All this does is make things way more complicated, because here is a scenario. So let's say your mediator is managing your transactions and it posts a message to the first service at the top and then the second one, and it's working on the third one, but we're asynchronous. So another request comes in for the top one. And so now it has to start stacking up the transactions that haven't finished yet versus the ones I'm still working on. So now there may be a queue of pending transactions in some of the domain services. Now, what if an asynchronous request comes in that's contingent upon the outcome of one of the other pending transactions that I have in my queue? And now my head explodes because I can't imagine all of the error scenarios and the ways that these asynchronous things will tangle up and mess up with each other. So this is pretty much a nightmare. So really high coupling, high complexity, low responsiveness, and low scalability. Probably not the characteristics you want in your architecture. But, you know, one of these has to be the worst possible combination. And here it is. We called it the horror story. And this is an architect going, wow, our epic sagas are slow. Have heard the way you make things fast is do both asynchronous and choreography. And this is extremely difficult to get right. I actually prevented one of our client projects from stumbling right into this anti-pattern recently, because now you don't have a mediator, but you still have asynchronous coordination for the complex workflow that you have. This is even worse than the fantasy fiction story that we saw before. This is essentially impossible to get right. So medium coupling, because we don't have a mediator, that knocks coupling down, but this is the worst complexity of any of them. And low responsiveness availability, because everything has to happen or not at all, and only medium scale and elasticity. So what a lot of developers and architects accidentally do is take the epic saga and then modify it in damaging ways. Here are ways to modify it in beneficial ways. The last two of these, the parallel saga and the anthology saga. Parallel saga is eventual consistency, async, but mediation. So again, this is what you think about when you think about asynchronous orchestration in microservices, because now the transactional boundaries at the service level, and this is just like mediated, but with asynchronous communication, which gives you higher scale. This still has some complexity around synchronization of, you know, pending transactions, et cetera. But the coupling here is low, the complexity is low, and responsiveness and scale are both high. Those are often the things that you want in an architecture like microservices. And finally, the last of these, the anthology saga, this is the exact opposite of an epic saga. This is the completely opposite side of the box from an epic saga, because this is eventually consistent, asynchronous, and choreographed. This is like the one we saw before, which is great for chain of responsibility or a chain of events that happen, only now we're doing asynchronous instead of synchronous. So it's even more scalable, but more complicated as well. So here, very low coupling. This is the lowest coupling you can get, because of the things that increase coupling, it has the lowest value of all of those, but high complexity because you don't have a mediator. And so doing error handling is very tough in this architecture. High responsiveness and the most scalable of any of our solutions. So what we did, let's recap here for a second. What we did was identify those three dimensions in distributed architecture, and notice that, you know, if you change this, those other two always change. And so having discovered that, let's build a matrix. And let's actually investigate what happens within this problem space as each of them change. And what you end up with is this. Now, we did each of those independently from one another, but when we collated them, we discovered some interesting things. And of course, these are all qualitative analyses. None of this is quantitative, because it's almost impossible to do quantitative analysis for architectures, because no two architectures are the same. They're all so different from one another, but you can do qualitative analysis. So what we did is for each one of these architectures, assess these values and then put them together in a matrix like this, and discovered some interesting things. One of which is that coupling and scale are exactly inversely proportional to one another. And that sort of makes sense intuitively, but once we've done the individual analyses and put them all together, it is an exact inverse relationship that the more coupling you have, the less scale you typically have. And that's informative because if you want higher scale, then you're going to go to the less coupled versions of these workflows that we have here. Notice what this allows you to do. I was talking about iterative design earlier. This is how you do iterative design in a distributed architecture. You don't have to implement every one of these solutions. What you need to do is figure out qualitatively how they impact one another, and it allows you to create a matrix like this. Now, we've identified 3 generic forces: communication, consistency, and coordination. Those are definitely not the only forces you have to think about. These are just a good starting point. So for a particular organization, maybe security is a big deal. And so you would add a security column and then figure out, when I make security stronger, what impact does it have on communication, consistency, and coordination? This is looking at that conjoined space and doing an analysis for, as I change this parameter, what impact qualitatively does it have on the other parts of my architecture? That's a good way to do modern trade-off analysis within distributed architectures. So that is basically the last of what I was going to talk about today. So I'll be happy to solicit any questions that you might have.
So Christy, I guess you scanned the list of questions.
Yeah, okay, sure. So the first question is, when breaking down the monolith, what mechanisms can you put in place so that you don't break the functionality across the different components?
Yep, that's a great question. And that's really the subject of my book, Building Evolutionary Architectures, because what you need to do there is build an architectural fitness function that protects whatever that characteristic is. So you put your architecture in a fragile state as you're doing that kind of restructure, because it can't happen instantaneously. And you got to make sure that while you're pulling 2 things apart, that somebody doesn't come along and make more connections. That's where an architectural fitness function comes into play. Look at a tool like ArcUnit in the Java world or NetArchTest in the .NET world, and it lets you write rules that you can run just like unit tests within your architecture to make structural rules. And they can be temporary rules because we're doing a migration or restructuring, and then those go away once you've got the thing fixed. So there are good mechanisms to help do that governance, and you really should do that governance, because as you're pulling things apart, you're structurally very vulnerable. So you don't want to actually make the problem temporarily worse.
Yep.
The next one would be when is increasing the response from 1.5 seconds to 4.5 seconds acceptable, so as to favor the breaking down into smaller components over increased latency? Okay, can we compute a threshold for this slowdown, or is it always a red flag that the components are too small / tightly coupled?
Well, so coupling is always a red flag, because, you know, what coupling means is if I change this, I have to change the other thing. And so that makes coordination more difficult. But, you know, I try to never say never or always in architecture. So is 4.5 seconds too slow? It depends. Everything is, it depends. If I have the sandwich ordering app that allows me to order a free sandwich for lunch in the office, and it takes 4.5 seconds to respond, I don't care. Nobody cares about that. I don't care about security. I don't care if people know what my sandwich order is for that. So, you know, responsiveness is not at all important for that. But if I'm in a high frequency trading environment, obviously that is. So the point of this is, though, and it's a good question, because the only one who can determine the value that a particular measure like that gives for your organization is you. Because I don't know anything about your architecture. In fact, nobody on earth knows enough details about your architecture to make an assessment like that, except you. So this is one of the struggles we have of getting people to implement fitness functions in architecture is because everybody wants to just download a tool and set 3 configuration parameters like, okay, all of my work is done. But nothing like that exists in architecture because everything is a snowflake in architecture. So you have to do some of your own building, but there's great value in doing that building. And it's actually very little work, but you get, consistent results from it.
Okay, the next question. So move this to put it a bit into an organizational context with multiple teams. How can we ensure modular integration, organizational scalability, and team coordination for a product with a distributed architecture and multiple teams? Do consumer-driven contracts help? Are there?
Yes, consumer-driven contracts help a lot. So an entire chapter in our book that I didn't go into today is contracts and how you build contracts between parts in a distributed architecture. And so this is one of the key lessons that we figured out in the terms of writing this book too, which is about institutional reuse. This is one of those things that almost every company gets wrong because they think that reuse is universally a good thing, but it's only sometimes a good thing. So the way you get to reusable assets in an enterprise is by abstraction. You notice that, oh, look, those 4 things do that same thing. We should abstract that into some common behavior so that we don't have 4 copies of that. We just have 1. But the utility of reuse is about rate of change, not abstraction. So in the scenario you just posed, if you want to build highly scalable teams, you have to prevent them from creating tight coupling points to each other. Because as a team, I can't constantly worry that some other change by another team is going to mysteriously break what I'm working on. That is not the secret to getting good, fast movement. A lot of companies think the secret to moving fast is use a lot of reusable assets, but it's the opposite. Because the more reusable assets I'm using, the more I have to slow down to coordinate around that reuse. Think about the things we do get good reuse out of. Operating systems, frameworks, libraries, all things with a very slow rate of change and a very formalized update process. Only for your internal code, if you could say those 2 things, should you reuse things widely. And that's why so many companies are into this idea of reuse at the platform level within a large enterprise. Because think about, so let's say I'm an integration architect and I want to expose some accounting information to other parts of my architecture. I could just open up the accounting tables to my integration architecture and say, here, just query those tables anytime you want. Is that a good integration architecture? No, it's brittle because now you make 1 change to a column somewhere in somebody's implementation and 40 things break. So the idea of building platforms is building an API that encapsulates the rate of change. The API almost never changes. Slow rate of change. That's where reuse is useful. Well-defined API can change rapidly inside, but the API, the semantics of the API, very slow rate of change, which enhances reuse. Reuse is only useful, particularly in distributed architectures, when it has a very slow rate of change. So you should never couple to domain concepts because they change too fast. And so that's why everybody's going to these very broad encapsulations at the platform level so that change can occur inside, but a very slow rate of change in the API that I use to access whatever that capability is.
We have just a couple of minutes left. Let's take some shorter questions. This one is interesting and very targeted to our subject. How do you decide when you need to make changes to an existing architecture, considering there is always a trade-off? How do you identify red flags?
Well, of course, it depends. There are a number of metrics you can use. In our Fundamentals of Software Architecture book, we talk about some holistic metrics like, things like cyclomatic complexity are always interesting because it tells you how complex your methods or functions are. But there's some really interesting metrics like distance from the main sequence, abstractness and instability. All three of those metrics are really good sort of holistic views of the code base as to how balanced they are between reuse versus abstraction. So distance from the main sequence, if you really tied me down and said you have one metric that you have to run to assess the quality of the code base, it would be distance from the main sequence, because it looks at the balance between a lot of interesting things in the code base. But a lot of this is going to be driven by what do you want out of this code base? How long should this code base be alive? If we're going to decommission it in 5 years, then I'm not going to bother restructuring it. But if this is the core part of the business that I'd like to be around 100 years, then I probably want to restructure it, make some improvements to it so that I can continue to enhance it and build it over time. Part of this too is, does your organization view software as overhead or strategic? Because if it's overhead, then your main driver is cost savings. And you would want not restructure an architecture. You'd try to squeeze every last dollar out of it before it falls over and dies. If software is strategic, you probably will want to restructure it because you need that to enhance your strategic vision moving forward into the ecosystem. So a lot of determiners help you make that decision.
Thank you. Another one, in terms of reducing coupling dependencies and promoting scalability, in distributed architectures, choreography is often preferred to orchestration. Are there any techniques that support the convergence of the product architecture in a team without filling in the architect role, like fitness functions? I think the question is trying to make an analogy between let's say, architectural process and the technology.
Yeah, I think that's a tortured metaphor. And I push back on this thing that you should prefer choreography and microservices. That's just wrong. It's just wrong. I hear this all the time, and it's just wrong. You've got to analyze the trade-offs. Try doing a complex workflow with choreography and get back to me when you've got all the errors and the boundary conditions worked out, and it'll be years. It depends. You can't make sweeping generalizations and say, prefer choreography. That's ridiculous. That's like saying volatility-based decomposition is the only thing you can do. One of the things I try to encourage architects not to do is don't evangelize things like choreography, because I can come up with 100 scenarios right now that choreography is really terrible for in distributed architecture. And when you evangelize things like that, it doesn't help your cause. It's really about trade-offs, analyzing trade-offs on either side. And I understand the kind of metaphorical mapping you're making there between orchestration and choreography, but we have a lot of sort of tortured metaphors in the software world, and sometimes they work pretty well and sometimes they're pretty tortured. And that one feels to me pretty tortured, because two things, so correlation does not imply causality, and that looks to me like correlation rather than causality.
Okay.
Mm-hmm. Looks like we are running out of time, so we will close it here. Thank you so much, Neal. There is a lot of new information, and we are looking forward to see your new book. I'm certain that most of us found out during the time lots of the situations that you covered in the new material. But it's really nice to have a unified framework, a structured way to think about these problems. So we're looking forward to see your books.
Yep, we hope this helps people, come to decisions more quickly in a much more objective way in the future, because people are churning around a lot, and I think this will help add some structure to that.
It will definitely help architects to iterate faster on the designs. Definitely.
Absolutely. Thank you very much for having me. I hope you enjoyed it, and I hope you learned some useful stuff.
Thank you. Thank you, everyone. And we are waiting for you to our next webinar, which is going to be Evolutionary Infrastructure on June 17th with Keith Morris. Looking forward to see you then.